Welcome to this training session on lithium-ion battery manufacturing. In this course, we will walk through the complete journey of how lithium-ion batteries are made, from the very beginning of raw material preparation, all the way to the final assembly and quality testing. Our goal is to help you understand each step of the process so you can connect your daily work in the factory to the bigger picture of battery production. Let's begin our journey from the front to the end of Li-ion battery manufacturing. We've now completed Step 1, electrode manufacturing. The electrodes are mixed, coated, calendared, slit, and finalized with tabs. They are now ready for the next major stage. Here we begin Step 2, cell assembly. This is where the electrodes, separator, and electrolyte come together to form the actual cell. In this section, we will look at the key processes of stacking or winding, packaging, tab welding, and electrolyte filling. These steps transform the individual components into a functioning battery cell. From this point forward, precision and cleanliness become even more critical, since we are now building the heart of the battery. Cell assembly, process overview. Now that the electrodes have been fully prepared, we proceed to cell assembly. This diagram illustrates the complete process, from slurry mixing and coating through to drying, calendaring, electrode cutting, and ultimately, cell assembly and final electrolyte filling. In this stage, the prepared electrodes are stacked or wound together with the separator, placed into the cell casing, and then filled with electrolyte under dry room conditions. This is the stage at which the separate electrode materials are combined into a complete, functioning battery cell. Cylindrical battery assembly. For cylindrical cells, we begin with the winding method. The cathode, anode, and two separator rolls are wound together to form what's called a jelly roll. Next, tab welding attaches aluminum tabs to the cathode and copper tabs to the anode. This ensures strong current collection points. The jelly roll is then placed into a cylindrical metal during the tab shaping and canning step. Tabs are bent, positioned, and secured by welding to maintain stability. Finally, electrolyte injection is performed in a vacuum environment. The electrolyte penetrates the jelly roll fully, and the can is sealed to complete the cylindrical cell. Pouch-type battery assembly. For pouch cells, assembly begins with the fabrication of a monocell, where multiple sheets of electrodes and separators are layered together. Then, using lamination and stacking methods, the half cells are pressed and stacked to achieve maximum packing efficiency and higher energy density. The stacks are then enclosed by a pouch film during the pouch case creation step. The film is pressed and welded to form electrode pockets and to secure the cell leads. Finally, in electrolyte injection, the liquid electrolyte is carefully filled into the electrode pores through dedicated gas pockets. The pouch is then sealed, completing the pouch-type cell assembly. Cell winding. Now we move into one of the most important steps in cell assembly, winding. In this process, the anode, separator, cathode, and another separator are stacked in layers and rolled together tightly. This rolled structure is often referred to as a jelly roll, as it resembles a rolled-up dessert. For cylindrical cells, this jelly roll is inserted directly into a metal can. In the past, the same winding method was also applied to prismatic cells. What's important here is precision. Each layer must align perfectly to avoid defects, and the winding tension must be consistent. If it's too loose, the layers may shift and cause internal shorts. If it's too tight, the electrodes can crack. So, when you see these rolls moving through the winding machine, remember that this step shapes the entire heart of the battery. Cell assembly, cell stacking. In this step, we look at one of the key approaches in cell assembly, cell stacking, also known as Z-shaped stacking. The process begins by cutting the cathode and anode foils into identical pieces. These foils are then stacked alternately, with separators placed between them to prevent direct contact between the two poles. The Z-shaped folding pattern ensures that the layers remain aligned and electrically isolated. This technique is widely used in pouch cells, as it enables efficient use of space and contributes to higher energy density while maintaining safety and structural integrity. Cell assembly, cell winding, and cell stacking. In lithium-ion battery manufacturing, two primary methods are employed to arrange electrodes and separators: cell winding and cell stacking. With winding technology, the anode, separator, and cathode are rolled together into a spiral shape, similar to a jelly roll. While this method is effective and widely used, especially in cylindrical cells, it presents problems in prismatic and pouch cells. The winding process creates curved edges inside the cell, leaving unused space and lowering the overall energy density. Over repeated charging and discharging, the electrodes expand unevenly, which can lead to deformation and a reduction in battery life. On the other hand, stacking technology arranges the electrodes and separators in flat, layered sheets. This method eliminates the curved edges and improves space utilization, providing about a 5% higher energy density compared to winding. Because the layers expand uniformly, stacking also reduces the risk of deformation and ensures a longer cycle life. For these reasons, major battery manufacturers are increasingly adopting stacking technology, particularly for prismatic and pouch cells, to enhance performance and durability. The illustrations here show the difference. Winding creates curved electrode paths with wasted space, while stacking produces straight, uniform layers that maximize efficiency and structural stability. Cell assembly, cell winding, and cell stacking. In cell assembly, electrode stacking and winding represent the two mainstream approaches for arranging electrodes and separators. While winding is widely used in cylindrical and prismatic cells, stacking is increasingly applied in pouch and prismatic cells due to higher space efficiency. However, the stacking process itself is highly complex, facing challenges such as low manufacturing efficiency, yield loss, and difficulties in quality control. To address these pain points, several types of stacking machines have been developed. Z-stacking machines, which stack electrodes one by one with separators in between. Stacking and slitting machines, that cut and arrange electrodes simultaneously for improved precision. Continuous thermal lamination stacking machines, which bond layers together with heat for higher throughput. Stacking and folding machines, a trade secret technology pioneered by LG, allowing improved efficiency and reliability. The schematic shown here highlights the main approaches. Single-sheet stacking and Z-stacking, widely used in pouch-type cells. Cylindrical winding, forming the classic jelly roll structure. And prismatic winding, used for rectangular cells, but with efficiency limitations compared to the stacking method. These technologies reflect the ongoing innovation in battery manufacturing aimed at balancing efficiency, quality, and energy density. This slide illustrates the first-generation cell electrode stacking, featuring two animations, single-sheet stacking and Z-folding with single-sheet electrodes. In the early stages of lithium-ion cell manufacturing, first-generation electrode stacking technologies were introduced. Two main methods were used. Single-sheet stacking. Each electrode sheet is individually selected and placed, with a separator in between. While this ensures alignment, it is extremely slow and inefficient. Z-folding with single electrode sheets. Electrodes are folded together with separators in a Z-shaped pattern. This method is slightly faster but introduces another problem. The separator tends to shift between the cathode and anode edges, creating the risk of misalignment and deformation. The key limitation of both methods is low productivity. The average stacking speed is about 0.5 seconds per piece. For a cell requiring 30 layers, that's 15 seconds to stack one cell, or roughly 4 cells per minute, 4 ppm. These inefficiencies highlighted the need for new generations of stacking technology with higher speed and improved precision. Cell assembly, cell winding, and cell stacking. Stacking and cutting integrated machines. This slide introduces the second generation of stacking technologies, stacking and cutting integrated machines. Unlike earlier processes that separated cathode and anode feeds, these advanced systems integrate cutting, stacking, and taping into a single streamlined line. The first animation accuracy. The second figure illustrates SK Innovation's Z-folding method, where separators and electrodes are folded together in a highly efficient sequence. Shows how electrodes and separators are cut and stacked in a single continuous process, minimizing handling steps and improving efficiency. These machines achieve remarkable speed and productivity. Some models can reach 0.075 seconds per piece, or 800 ppm, while others operate at 0.15 seconds per piece, or 400 ppm. This represents a significant leap from the first-generation stacking speeds, reducing cycle time while maintaining alignment and quality. By integrating multiple steps into one piece of equipment, This approach addresses the key challenges of efficiency, yield, and cost in large-scale cell assembly. This slide introduces the continuous thermal lamination stacking machine, the third-generation approach to electrode stacking. Unlike earlier methods, this machine combines multiple steps into a single, continuous line. It integrates electrode slitting and manufacturing from the front end, as well as stacking, thermal lamination, and calendaring. As shown in the schematic, electrodes and separators are fed together, preheated, and pressed through lamination rollers, creating a tightly bonded electrode stack. Because several procedures are merged into one system, this machine not only increases throughput, but also saves a significant amount of factory floor space. However, it is essential to note that the technology remains relatively immature and large-scale industrial adoption is ongoing. In short, continuous lamination stacking represents a promising step toward higher efficiency and integration in Li-ion battery manufacturing, but it remains an evolving technology. In this video, we see an automatic lithium-ion battery electrode stacking machine in action. This equipment represents one of the more advanced approaches to cell assembly. As the video begins, you can see the electrode sheets and separators being precisely fed into the machine. The system aligns each layer with high accuracy, ensuring that the anode, separator, and cathode are stacked with precise alignment. Next, the automatic separator wrapping function is demonstrated. After the electrode sheets are stacked, the separator material is folded around the stack, creating a secure wrap that keeps the cell layers insulated. Following this, the process continues with the application of adhesive tape, which is automatically applied to hold the stacked and wrapped electrodes firmly in place. This prevents shifting or misalignment as the stacks are transferred to the next stage of assembly. Throughout the demonstration, notice how the system is fully automated, minimizing human intervention, increasing throughput, and significantly reducing the risk of defects caused by manual handling. By the end of the video, you will see a fully prepared electrode stack, tightly wrapped and stabilized, ready to move on to the next stage of the cell assembly process, such as electrolyte injection or casing. This video highlights how automation not only improves efficiency, but also enhances precision, safety, and consistency, essential factors for producing high-quality lithium-ion batteries. Winding stacking, LG and Mann's manufacturing patented technology, we now move on to the most advanced and efficient stacking approach. The winding stacking process, jointly developed and patented by LG and Mann's manufacturing. This method combines the strengths of both winding and stacking technologies, resulting in the fastest and most efficient production speed among current techniques. The process begins by preparing a bicell unit consisting of one cathode foil, one anode foil, and one separator sheet, each cut to standard sizes. These are then stacked together into bicells, which are further stacked into multi-layered assemblies. A critical feature of this process is the use of an SRS, safety reinforced separator. This is a ceramic-coated separator that is heat-treated to enhance tensile strength, improving both durability and safety performance. The animation on the left compares winding with stack and folding, showing the structural differences between the two. The diagram on the right illustrates how individual foils and separator sheets are combined to form bicells, which are then stacked to build the final electrode structure. This patented method is widely regarded as the benchmark for high-efficiency lithium-ion battery cell production. After the electrode stack or jelly roll has been assembled and placed into its housing, whether a pouch or a metal can, the next critical step is filling the electrolyte. This process is carried out using high-precision needles to inject the electrolyte into the cell. Because the electrolyte is highly reactive, especially with moisture, this step must be performed under extremely controlled conditions. Even trace amounts of water can lead to the formation of hydrofluoric acid and the release of toxic gases. For this reason, the process is conducted in ultra-dry rooms with minimal humidity. Once the electrolyte is filled, the injection port is sealed, and the cell undergoes a wetting step. This involves applying alternating pressure and vacuum cycles, often with the use of an inert gas, to help the electrolyte penetrate the porous electrodes through capillary action. The video you see here, taken inside LG Chem's factory, demonstrates the precision and automation required for safe and efficient electrolyte filling in modern battery production. This concludes Step 2 for cell assembly. Thank you.